Derivative formulas. In the previous section, we looked at how we could define a derivative by using limits. We were able to find various functions and their derivatives by using the limit as h goes to 0 of f of x plus h minus f of x over h. Let's look at this for a couple more examples, and then we'll recap the ones we've already looked at. So let's suppose we want to find the derivative of a constant, f of x equals c. So remember, if your function is a constant, that means you have something like y equals 5 or y equals -2. If it's constant, it's just a straight line that's horizontal. So we're trying to find the derivative of this function. So again, we're going to apply our formula, which we see down here. If you plug in an x plus h into f of x equals c, you just get c because there is no x to plug into. Similarly, f of x also equals c. So we end up with the limit as h goes to 0 of c minus c divided by h. Well, since c minus c equals 0 and h doesn't ever equal 0, it just gets really close, 0 divided by anything is always 0. So we find that if our function is just a constant by itself with no variable in it, then the derivative is 0. And this makes sense because remember, the derivative is the slope of the tangent line. A tangent line to a linear function like we have here is going to lie on the line, which means it's going to have the same slope as the function itself. And you can see here that whenever we have a constant, it's a horizontal line. And we know that the slope of a horizontal line is always 0 for every point. Therefore, it makes sense that if we were to find the derivative of a constant, it would be 0 everywhere. Let's look at another. Suppose we want to find the derivative of a linear function. So remember, a linear function is a line that has some sort of slope m. Now, here, like before, our tangent lines will lie on the line, which means every single tangent line is going to have the same slope as the line itself. Therefore, the slope of every single tangent line is going to be m. But let's show this a little more carefully. So again, starting with our definition of derivative, if we plug in an x plus h into mx, we get m times x plus h minus f of x, which is mx, divided by h. If we distribute the m, we have mx plus mh minus mx. So we have an mx and a minus mx, so those will cancel. And we're left with mx over h. So here, the h's will cancel. And we end up with the limit as h goes to 0 of m. Since there's no h's left, that just equals m. So what that tells me is that if I have a function that's m times x, that the derivative is just that m. And remember, m is just a constant. It's the number that represents the slope of the line. So now we have two new statements from our definition to add to the two that we'd previously looked at. So let's remember the two that we'd already calculated. So earlier in the term, we used the definition of derivative to find f of x equals x squared has a derivative of 2x, which we can also write as 2x to the 1. Additionally, we use the definition of derivative to find that the derivative of x cubed was 3x squared. So when we add those to the two that we just talked about, the derivative of a constant and the derivative of mx, there's a pattern that begins to form for polynomials and power functions. So again, these are functions where x is raised to a power. If we do enough of these, we see that the derivative of a function x to the p has the form px to the p minus 1. So what that means is when I have a function like x cubed, the 3 comes down in front, the power comes down in front, and then we subtract 1 from the power. When we have patterns, that's how we get formulas. So in this section, we're able to find and use various formulas for derivatives so that we no longer have to calculate them by approximating really close to the point. We'll now have a way to find the formulas exactly so that we will no longer have an approximation, but an exact answer. So let's look at a table of all the formulas we know so far from the patterns that we've discovered. So far, our derivative formula list is comprised of 3 functions. So here we have a constant, the derivative is 0. If we have a constant times x, the derivative is just that constant. And if we have x raised to some power that we're calling p, then the derivative is px to the p minus 1. So we're going to be adding to this formula list for the rest of this chapter, but we're going to start with these 3 formulas and we're going to practice finding derivatives using these formulas. Remember, c, m, and p all represent constants here, and x is our variable. Example 1. Use the formulas to find each of the following derivatives. So for part A, I have f of x equals 7. That's a constant. That means that if I were to take the derivative of that, I would get 0, because the derivative of any constant that's by itself is just 0. For B, I have 10x. So that's in the form mx. I have a number times x, which means when I take the derivative, it's just that number. Notice that a and b are different. A is a constant that's by itself, whereas b is a constant attached to the variable. So these result in different outcomes. Part C, I have x squared. So the rule for polynomials and power functions is that the 2 will come down and I will subtract 1 from the power. So I get 2x to the 1. Part D, I'm going to use the same rule, only now I have a power of 5. So the 5 comes down and I subtract 1 from the power, 5x to the 4th. For part E, I have to be extra careful here because my power is negative. So I get negative 4x to the negative 5. So if you have a negative 4 and you subtract 1 from the power, you get more negative. So you get negative 5. If we have x to the 2/3, that means the 2/3 will come down in front. And then again, we're going to subtract 1 from the power. 2/3 minus 1 gives me negative 1/3. So again, be careful with fractions. And then finally, our last example here, G, we have x to the negative 4/5. So the negative 4/5 comes down in front, and then we subtract 1 from the power. Negative 4/5 minus 1 is negative 9/5. So here, applying the rules that we have so far, we're able to take the derivative of all sorts of functions where our variable is in the base and we have a numeric power. Now your variable doesn't have to be x. We could have used f of t or c of q. If we change the variable, the rule doesn't change. But here, we're using x just to get us started and used to these formulas.